Well, how are you doing? Okay, this video is going to be based around mostly perspective and misunderstandings people on our opposing side have about it, and misunderstandings they have about their own paradigm. Now, where I am at the moment, there is a roof close to me with rain dripping down on it and landing on it. Hopefully, it's not coming into the recording too much. Okay, this diagram here and this one were presented to Nathan on one of the Discord servers recently. And I'm going to go over, I'm focusing on this diagram here, presented by somebody who's on the opposing side. I just want to go through these two here first, and then I'm going to move up to this one, right? So here he's showing, right, measuring the angle, right, elevation angle to a tree, right? So he has the baseline, there he is, there's his theodolite or whatever. Here is the baseline, which is a horizontal, right, distance between his theodolite and the tree. He has a horizontal from the lens of the theodolite out to meet this point on the tree, showing that, and remember, this is as far as I know, this person is a baller on the opposing side. So he's showing that that's where his eye line is on the tree, because it's the exact height between the base of his theodolite and the lens, right? Base of the tree up to there, that's the exact height of his lens. So this is his delta height then, right? So his angle goes up to there, and this is his delta height. So that's an horizontal out to meet the tree, height up to the top of the tree, and line back to the lens. That is a right angle triangle because it's an elevation angle. And as I've said so many times in the past, and I've shown and I've proven in very recent videos and in the past, that an elevation angle is always a right angle triangle. Always, right? Now, with celestial navigation, with the celestials, you don't do trigonometry with the right angle triangle. It's something that seems to completely, I don't think any baller can understand it. They seem to not be able to understand it. I think our opposing side don't have either they can't understand it because once they do, it causes them problems mentally and emotionally, or they just don't have the intellect. They just can't understand it. Their intellect, it just doesn't. They can't do it. That's. I hate to say that. I hate to say that about people, but it seems to me that it's so simple. What the answer is, yet they can't understand it. They can't understand how an elevation angle is a right angle triangle, and they can't understand then how how in celestial navigation you don't solve for the right angle triangle. You're using a right angle triangle, that's your elevation angle, but you don't use trigonometry. You're not solving for the right angle triangle. You're only solving for the horizontal distance, which would be this distance between here, the legs of that theodolite there, and the base of the tree. If you wanted to give a comparison distance, it's only the horizontal distance that you're gaining via the angle to the celestial body. You're not using length of sides and all this. It's not what you're doing. But anyway, that's not what this video is about, but I just had to show that this is someone who's a baller who understands this, but yet if the person ended up in a conversation with me about celestial navigation, they wouldn't be able to understand it. How they use their right angle triangles with the celestials. Now, of course, they use it when it comes to a lighthouse or something. They will solve for the right angle triangle when it comes to a lighthouse of a known height, whatever else. Yeah, of course they'll do that, but not with the celestial bodies. You don't do that. Anyway, we'll move on from that because that's obviously a point of great problems for our opposition. They just can't get. They don't understand what a statuate mile is. It's a very complicated issue for them. I don't know if they'll ever overcome it. I think they'll always be stuck not understanding how the distance, how one degree of angular distance was found to be to Polaris. I don't think they'll ever understand that. I think they'll constantly not understand that. They won't understand that nautical miles are horizontals because statuate miles are horizontals. Do you know what I mean? That's how it was worked out. They worked out what 69.04 horizontal statute miles were. How that gave them 1 degree of angular change to Polaris. That required, sea level to be 69.04 horizontal miles of horizontal. Do you know what I mean? It's crazy they can't get that. It's so simple. The whole process is so simple, but it escapes them. I think I can't say it's all intellect because obviously it's a case of if they accepted that their whole paradigm is over. But obviously with some of them it is. They just really cannot understand it. They can't get that. It boggles their mind. They must lay awake at night looking at the ceiling, in the bed, kind of going, how are they doing that? I mean, the confusion for them is phenomenal. Anyway, we'll move on with this. I just wanted to show this here, just to show that this is an elevation angle this is used in surveying, right? So this person understands, the person made these, they understand surveying is parallel verticals, because this is a vertical here. This opposite of the right angle triangle for the elevation angle, and they're a zenith. That's two parallel verticals, and these are two parallel horizontals. So this person understands this, right? Then I'll go up to this one. Here we have again, this is about grade. So they have run distance, which is your horizontal, and rise distance, which is vertical. And their zenith will be up here, so that would be parallel verticals, And if they made a depression angle with this, it would be parallel horizontals then as well, But this is your slope grade. So this is an elevation angle, once again a right angle triangle. Yet, as I said, our opposition keep on claiming that elevation angles are not right angle triangles. Even though you take elevation angles, they're claiming in celestial navigation that there is no right angle triangles with the celestial bodies. Yet they'll still call them an elevation angle. When an elevation angle is arctan rise run equal elevation angle. Do you know what I mean? It's like this, right angle triangle. Do you know what I mean? So here you have rise and run, and then slope gradient. That's a right angle triangle. They use the same thing in celestial navigation with the celestials. There's no great mystery, it's just these people don't understand it. They can't get it. It's beyond them. It's beyond them to understand that. They in their minds this can be an elevation angle, and the angle they take to a celestial body, even though that's also an elevation angle, is some other thing. I mean, I don't know how they can do this. How can it be some other thing? If you know what I mean, how can it be some other? A Volkswagen is a Volkswagen. Do you know what I mean? It is what it is. One Volkswagen is a Volkswagen, and another Volkswagen is also another Volkswagen. Do you know what I mean? I don't get that. You know what I mean? But anyway, these people have wicked problems with this. But what can you do? You can't solve all these people's problems for them. It's up to themselves. Anyway, that's just showing that this person understands horizontals and verticals, and the person who presented these things. I think I recognize the name of the guy, but I won't give his name because I don't have his full name. But the main thing I'm focusing on here is this. He claimed, right, this is supposed to be some kind of an angular size measurement from someone in Mount Scott Crater Lake, Oregon, right, taking an angle to Mount Shasta, California. Now, Mount Scott, or the person in Mount Scott, was 8,934 feet high. Mount Shasta is 14,179 feet, right? But what they seem to do is take a dip angle to the prospective size of Mount Shasta, right? Now, it's a bit crazy. They're 105 miles away, and the extra height of Mount Shasta above wherever they're at, let's say, I'm not sure if Mount Scott is 8,934 feet high, but their elevation, let's just say, was 8,934 feet high. But let's just say it is, right? Then the extra amount higher that Mount Shasta is 5,245 feet. So that would be this much. But they took a dip angle to the prospective size of Mount Shasta. And for some reason or another, to them, that meant that it was gone over Earth curve. How they come up with this crazy nonsense, I don't know, because you don't take an angular size like that. You take an angular size of the whole mountain, or if you're going to take an angular size of a part of the mountain, you can do that. But the problem they have is they're an angular size measurement, right, or a measurement like this. This is a measurement of perspective. So they're including perspective in their measurement, but then they're denying it by claiming that they took a dip angle, right? Things change with angular size in the distance. So they want things to change in angular size in the distance, but then they don't want it. I think they were expecting to bring a straight line out here, and the straight line from the theodolite would meet Mount Shasta about here in a straight line, right? Now, that is what's happening, but because of perspective, things appear to be slanted down. They're not actually slanted, they just appear that way. But this person was trying to take an angular size of this part, the 5,245 feet that Mount Shasta is higher than Mount Scott and Crater Lake. Like, this is crazy on so many levels. Because how could they take an angular size, which is perspective, and then try and make perspective not be there by hoping that this mountain will be up in the air above them? I don't know what. I don't know what were they expecting to get. Like, were they expecting to get an angle up to the top of Mount Shasta? Even like the only way they're going to get an angle up to the top of Mount Shasta is that if both mountains don't angularly change in size. Do you know what I mean? It's like, how are you going to have an angle up to the top of Mount Shasta and expect Mount Shasta to change an angular size at the same time? That's crazy. You're taking an angle to the top of Mount Shasta. This angle here is an angle to the perspective size of Mount Shasta. Because his straight line of sight would have been, if you follow my mouse here, would have been to here. That would actually have been his horizontal. If this is Mount Shasta, it meant to be Mount Shasta's angular size, this would have been his horizontal to there. It wouldn't have appeared horizontal because because in perspective, when horizontal comes out from your eye line, it appears to slant down, right? In actuality, you don't realize it, but in actuality, it appears to slant down. The reason it appears to slant down is because over this distance of 105 miles, the baseline between these two mountains stayed equal. So this baseline here, right at the base of the Mount Shasta, that didn't come up. They keep Mount Shasta high up in the sky. That stayed as it is. As over distance, what happens is the top of something high with angular change appears to come down. That's what happens. The proof of this is dip correction, right, in celestial navigation. Because dip correction, right, it might look to you, right, when you're close to when you're like only maybe 10, 20, 30 feet, whatever it is, above the water, right, out at sea, and you're seeing the horizon, right. The horizon can appear at first glance to be, almost at your eye line, right, but it's not. Because the water that's underneath your boat is in a horizontal line with the water that's at the horizon. So if your eye line is 30 or 40 feet or whatever, 20 feet above the water that's underneath your boat, then it's also 20, 30 feet, whatever, above the water at the horizon. So there's no way that that water that's at the horizon is going to rise up to your eye line. Because in our class, they'll try and put a straight line across the screen. And they'll try and make everything come up from the bottom to meet it, and everything from the top come down to meet it. But in reality, we don't have a line right across the center of our view, right, when we're talking about perspective. Because the Earth doesn't come up. It will appear with distance and with elevation, it will appear to stretch out further. That's what it does. It appears to stretch out. But the sky comes down much more than the ground appears to stretch out and rise. The sky comes down much more than any ground will appear to rise up. Because the ground is just staying constant. All that's changing is that the angular size of something, or it's the angle to a cloud or something, will appear, the cloud appears to reach the horizon, but it's not really reaching anything. It's just a perspective thing. It's purely optical, just an optical phenomenon. But this person here thought that they were, by taking a dip angle, what they thought was a dip angle to the prospective size of Mount Shasta. Now, I don't know if any of this actually happened, right? This is just a story they give, right? This is nonsense, right? But this, I just feel like it. I feel like it needs to be pulled apart because it is total nonsense. But this person expected Mount Shasta to not change in angular size while also taking angular size measurements. I know what I mean, of the top of it. And I don't know why you would be trying to take an angular size measurement of the top of it. So what they decreed was that they took a dip angle of 0.10681, right, degrees. And to them, that meant that there was an extra 1,034 feet. And they came up with this crazy 6,279 feet, right? This is what they came up with. So what they're essentially saying is that it's hard to figure out what they're essentially saying because it's such nonsense. But they're essentially trying to say that the top of Mount Shasta is 6,279 feet below them when it should only be 5,245 feet, when it shouldn't be below 5,245 feet below them either. I mean, this is crazy. This whole thing is so crazy on so many levels. But either way, I'll just dispel it. First things first, right? Most important. In our curve maths, right, and the globe paradigm, there is no perspective accounted for. It is not part of our curve maths. It is not part of any calculation of our curve, regardless of what way these people, some of these frauds like Walter Bislin wants to add in angular size, change the things after he's added in our curve, make West up to a point two. They're all frauds. There is no angular size change, right? There is no optical drop, angular size change, visual occultation, also known as photographic occultation. None of these perspective effects exist within our curve maths. They do exist in reality, but they don't exist in our curve maths. And I brought out a video some while ago. I'll link a few videos below in the description. I brought out a video some while ago where I showed where if perspective existed and our curve existed, then a 6-foot object would disappear at 1.8 miles away from an observer. Now that doesn't happen. A 6-foot object, its angular size will reach 0.02 degrees, which is the resolution limit of the human eye, the average resolution limit of the average human eye at 3 miles away. Now it just happens that a 6-foot object will be gone down behind the curve of a globe Earth 6 miles away. So which is it? Because if you're claiming that our curve exists, then you are ipso facto, right, claiming that perspective doesn't. If you're claiming perspective exists, which this person obviously does because they're taking angular size measurements, well, it appears they are, then our curve doesn't exist. So this person, I don't know what kind of a silly, useless gotcha they thought this was going to be when they're trying to calculate some kind of 6,279 feet on of I don't know what they're really at. It's ridiculous. But the fact that they're accepting that there's an angular size change and these things happen means for that person, our curve and a globe Earth does not exist. So if you go out taking angles and angular sizes and you accept that when a car drives away from you, it changes in angular size, or when you move away from a high object, it changes in angular size, that is the end of globe Earth. It finishes right there. So I'm just going to go on and I'm just going to show some stuff. Right, so first of all, I'm going to show what the effect of optical drop is. Now, I've gone through this many times in the past. No. First of all, I'm going to show something here, right? Now, there is the distance, 105 miles in feet. That's 554,400 feet, right? That's 105 miles. That's the distance between the two mountains from Crater Lake to Mount Shasta. There's Mount Shasta's size. It's 14,179 feet. that makes Mount Shasta, that would means Mount Shasta has an angular size from that distance of 1.46 degrees. Now, how is somebody standing, right, on Crater Lake, in Mount Scott and Crater Lake, looking at Mount Shasta that has an angular size of 1.46 degrees? How the hell are they expecting, right, how are they expecting Mount Shasta to be up in the air here? Or whatever, I don't know what they were expecting. Whatever crazy nonsense they're at here, I don't know what they're at or what kind of silly nonsense that's going on in their head. All I know is that Mount Shasta has an angular size of 1.46 degrees at that distance. And just so you know, angular size calculations are orthographic calculations. So they're not even correct with perspective. Perspective it's only a basic calculation, because perspective will often show an object smaller than an angular size. The angular size is just an orthographic calculation of size at distance. That's what it is. So it's not even fully matching. Like it's an attempt to match perspective, right? That's what it is. But it doesn't match perspective. A lot of the time it doesn't match perspective, but it's an attempt to match it. But the point being is that if this mountain here is 1.46 degrees at 105 miles away, how is this person expecting to have a straight line out from let's say from their theodolite, and to meet Mount Shasta 3/4 way up, if they were just putting it a straight line out? Now, they actually, see, this is the thing, they actually were. This is the thing, because when that line of sight came out from their theodolite, it actually was meeting Mount Shasta at this point. But, right, they are not understanding the Mount Shasta at that point as an angular size. So they think, right, because they're not thinking straight, that it's going over the top of Mount Shasta. Right, this is what they think is happening, that it's going over the top of Mount Shasta, when it's not going over the top of Mount Shasta. Your straight line out is still hitting Mount Shasta here. It just doesn't appear that way with the naked eye, because of perspective. It would appear that the line is coming down at an angle, right? Down at an angle. This is why they come up with this dip angle, right? Right? If they were to actually try, right? So this dip angle is wrong, because there was no need for that to be put in. This line here, right, this horizontal line out from the theodolite, was meeting Mount Shasta at this point. It's just due to perspective, it didn't appear that way. It appeared to the person that they were looking up higher than they really were. They were not. They weren't doing that. They were actually meeting Mount Shasta at this point. But because Mount Shasta had an angular size of 1.46 degrees, it appeared, not actual, appeared. Take this in, ballers. Appeared. It wasn't actual. APPEARED. Appeared to be different. Okay? So, the angular size then of Crater Lake Mountain, or the mountain of Crater Lake, is 8,934, right, feet. And it has an angular size of 0.92 degrees at that distance, right? So if we add on, right, so we add on their crazy 6,279 feet. This is just going to show how crazy it is. So they're 6,279 feet, right, which is an angular size of 0.64891. So we're going to add that on to the height, their angular size of the Crater Lake Mountain, right, in Oregon, which is 0.92. So when I add on this extra feet, this 6,279 they come up with, we'll add that on in angular size. So plus 0.64891 equals 1.57. So that means it's they're claiming that the angular size of Mount Shasta at that distance is not 1.46. They're claiming that Mount Shasta has an angular size of 1.5722. Now, let me just try something here, right? So 15 right? So angle degrees, sorry, angle degrees, sorry, just try that, 1.6. So they're claiming that Mount Shasta. Now that's not exactly it; it's a little bit less. So if I just go back to 2, let's just say calculate again, right? Back to 15530, right? 15230. Right, there we go. So they're claiming, this is how ridiculous they are. This person or whoever is involved is claiming that Mount Shasta is 15,200 feet, when Mount Shasta isn't. Mount Shasta was 14,000 and whatever feet. So that's what they're claiming. They're actually claiming that, without realizing it, that they're actually claiming that Mount Shasta is 15,200 feet as opposed to 14,179 feet. That's over 1,000 feet higher. Their calculations are so screwed up that they're claiming that Mount Shasta is over 1,000 feet higher than it really is. This is how bizarre and messed up these people are, because they can't understand that in a straight line out from your theodolite is meeting Mount Shasta at this point. It just doesn't appear like it, because what would happen is that it would appear, if it had a straight line, it would appear to be going down, but it's not, just because the angular size is changing. And angular size brings the top of things down towards the bottom. That's what it does. So this is just a total unbelievable confusion on the part of these people or whoever was doing this. So just to show this, right? Now, here we have a mountain, right? Right, here we have. And if I just move this in to here, there is a 75.96 degree angle to the top of that mountain, right? Now, if I was standing here, this line would represent my eye line looking to the top of the mountain. Look how much my head is tilted up, right? Now, if I come back to here, then I have a 38.65 degree angle to the top of the mountain, right? Y angle, right? Orthographically. But my head then is not tilted up here like this angle, it's like this. And if I come back away from the mountain then, back to, let's say 26 here, I only have a 17 degree angle to the top of the mountain. Now the thing with that is, orthographically, what's happening is this is staying equal orthographically, right? So even though the angle here line is it appears to be changing, right? It's rising and going down. The mountain diagram here is staying the same because it's orthographic. There's no angular size change here happening. You would have to change the size of this mountain in accordance with the distance to somewhat match reality. You know what I mean? Match what you would see in reality. This is not changing orthographically, but your line of sight to the top of it is changing because as you move away, but the base of it is staying equal, right? So if I just do this, sorry now. So as you move away, the angle to the top of the mountain will change. So now it's only a 7 degree angle, right? Now the mountain here didn't change in actual size, but in angular size, right, for the observer, it would appear to be down here, a small little mountain. It would appear like the top of the mountain came down, because that's how it appears to the observer, that the top, right, the decrease in angular size in the vertical is always top down. So the mountain appears to be getting smaller this way. It might appear to be getting smaller horizontally, as in width, but it's definitely appearing to get smaller this way for the observer. So this is what that person, whoever made the thing, can't understand. That there's a top-down change, that happens. This is just a natural thing that happens as part of our eyesight, part of perspective. Now, as I said, once they accept perspective, then that's the end of our curve, because perspective is what they hijacked to come up with a curve, basically. But, because they hijacked the celestial dome model, which is based off of flat Earth elevation angles to Polaris. So elevation angles, that's perspective angles, because angular sizes and anything to do with angles is perspective, in that way. You're talking vertically. But as you can see, if I put myself standing when I was in towards here, I had a 75-degree pitch up to the top of the mountain. But out here, I only have a 6.5 degree. So I'm not looking, my eyes aren't looking. If you right now look up towards the top, of up towards where the wall meets the ceiling in your room, whatever room you're in, and now bring your eye line down, your feet didn't change, everything else didn't change. All that changed was the pitch of your eye line to what appeared to be the top, because you moved away from it. That's what a change in perspective, angular size is. That's what it is. Now, I'm going to show some examples here, right? This is optical drop, right? Now, I've detailed this from years ago, shown this and proven it. I've shown it in real world. I'll link a video on it each showing optical drop, all these different real world examples. It's just something we see all the time, but it's what was called R-curve, and they've tried to hijack it for a long time now, and they don't want to accept this effect. Even though I've shown it, I've proven it, I've detailed it, shown it in the real world, but they don't want to accept it because this is what was hijacked and called R-curve. And this is exactly what this guy is trying to hijack there with these diagrams and call R-curve, even though he's using perspective. So, as you can see, right, 0.0, there's no tilt forward and back. The 0.4 degrees here, that'll change 0.3 to 0.4. That might change little bits, but that's because of the friction on the ground. The table itself has a slight tilt to the right of 0.4 degrees, but there's no tilt. My center of my lens is exactly 0.0, so it's making a parallel line, right, as I showed earlier, right? So parallel line with the surface. So this is center of my lens here, and at the bottom here, that's the table, right? So that's what I'm doing here, right? And this object here, this is a phone charger, and this part here is actually slightly higher than the center of my lens. If I move it in, on that I have to go back, move it in a little bit, as you can see now, but I'm keeping it kind of so I'm matching it up with the center of my lens. If I move it right in, it'll be blurry, but also these lines will be higher than the center lines. So I then move it back out, and right, here we go. As you can see, it was above, the lines next to that were above my center lines there, but as I move it back, what happens is it appears that, as you can see, the part there that actually in actuality is higher than my center lens, right, that appears to drop. Yet the table surface stays equal, right? That's not going up or down, but the thing that appeared to be higher than my lens, or is actually higher than my lens, appears to drop only because of optical drop. It's just a perspective, right? And I bring it back in, just bring it back to there, but it's a little bit. Now, you can kind of see it, right? Now, there it is there. If I move it in again, these lines will go above that, but that's okay, because it doesn't matter if it's above it or equal with it. The point is that at this moment, because the point is that this effect happens. Now, a lot of people argued against this effect. They didn't realize what was happening, and I tried to point out you have to make the center of your lens parallel with the surface. Because in reality, when we're looking at something, we're not trying to focus our eyes on the top of something or at some point on something. We're just looking forward. That's all we're doing. So basically, when we're looking forward, we're looking in a horizontal. So that's why when a ship moves away from you and you're looking out over the water and you see a ship moving away from you, it appears to be going down, but it's not going down. It's just that the top of it is going towards the sea because of perspective. That's all that's happening. It's purely perspective. The same with large buildings. That's why the large buildings appear to shrink in the distance, is purely perspective. This is all it is. To show this again in another demonstration, these are old demonstrations now, because I have older ones again than this, because this is something I've been detailing for years and years and years. But here is a demonstration with a laser, right? So as you can see, that laser, that light is above my center lens. Once again, 0.0, no tilt to my center lens. It's making a parallel with the surface. So it's two parallel lines. As I move this away, it appears to go below it, right? Here's another one, different filter, moving it in, and appears to go above it, and back out again. And as you can see, just as it gets to there, right? As it gets to there, because it's light and because there's a shine, and it can reflect off of this, it nearly looks like the sun on the water. That's what, right? So it gives that effect. Here it is again, and here you can really see it's like the sun on the water with this filter. It really looks like, as you get to there, you can see the amalgamation that's happening. Now, obviously, it's not. That's a laser. It's going in a straight line, right? And I've shown all this in the past. I've shown my setup. These are demos from years ago. Showing all my setup there. This is not really touching the table. It's still above the center line of my scope here, but it just appears that way over distance. That's all it is, right? Here's another one, right, with this filter. This is a different filter again. Here's another one. As I move it in, you can see it. So you get the idea. That's right. That's all it is. That's optical drop. This is a natural effect that we see in the world all the time. So if we look at some, never did maths for this before. I just did a little bit here, right? Now, the lens it's an iPhone 5 I'm using, right? The lens of it is 9 millimeters. I think it's 9 millimeters when it's turned flat onto its flat side. It's 9 millimeters off the surface, right? Now, something I have to talk about with this, right? This is something that people thought they were debunking because they were using cameras with a much higher focal length, right? This is the focal length of the iPhone 5 lens is like 3 or 4 mil, something like that, right? Whereas I have a Panasonic camera, and it's like I don't know, a couple of hundred, right, mil or something like that. So the problem is that if I use my Panasonic camera, which has a much bigger focal length than my iPhone camera, than the older iPhone I have, right? If I use that, what will happen is I won't see this effect over a short distance, but I will see the effect over a greater distance, which I show in real life, which I've shown in real life with my Panasonic camera. So the problem is that if you're going to use a camera that has a high focal length over a short distance, you're going to need more than the distance of your room. You're going to need a bigger distance, a real world distance. This is the thing. So you won't see this happen over a short distance, over like a couple of feet like this with a camera with a high focal length. You won't see that because the distance, it's a distance focal length ratio. That's how it works. Now with the human eye, obviously, you know what I mean? What's the focal length of the human eye? It's a crazy question. But with the human eye, with the way I'm no human eye expert, but I know what perspective is. I know everyone else knows what it is. But people are often confused. As you can see, right, I'm just going to show. See the base of that kitchen roll I have here that I have the light shining onto. That's not going up or down, right? Now that might be going. Actually, that might actually be going. That might be. No, it's not. That's going up. That's not going up or down. I was thinking of something there. It's the wrong table. That's not going up or down. That's staying constant. But the light appears to be going down towards that because that's what happens. The above comes down towards the below, right? Way more than the below can appear to go towards the above, right? That's the way it is. So it's only apparent. That's all it is. So what's happening here is purely an apparent effect that we see all the time in the world. But people in our class want to put this line here up here. It's like in the center of the screen. That's our class. That's not real perspective, right? In reality, right, things come down towards the base. That's what they do. Down towards the water, down towards the land. You know, they don't actually come down. They only appear to. And this is that diagram earlier. This is the problem. When it's here, they're taking an angle down to the top of this, not realizing that this line here is actually here. That's where it is. This line I have going across here. In a horizontal, if you were to see this orthographically, in a horizontal, it would be here, right? But they think they're taking a dip angle to, if this is Mount Shasta, to hit to this, they think they're taking a dip angle down to this, not realizing there is no dip angle because they're horizontal line is actually here. So they just don't get that. Do you know what I mean? They don't get that their horizontal line is actually there, right? If this is Mount Shasta, then the horizontal line is somewhere here because it's about a third way down. So Mount Shasta is an extra third bigger than the Crater Lake Mountain in Oregon. So Mount Scott. So that would mean that this horizontal line would actually be here. If this was Mount Shasta up from the table here up to the top of the light, then their line would be right there. But they can't understand that. They think that they're taking a dip angle down to this. It's like, you're not taking a dip angle down to there. What you're doing is you're taking a dip angle down to here, not realizing that that's what's actually going on. You're not taking a dip angle to the top of that because your horizontal is already below this line here. Your horizontal, from my horizontal right there, is below the top of this light. It's already down here. Or down here, actually. It's way down here. But it appears that it's not because of perspective. It only appears that way. It's purely perspective. That's it. Now, the lens of the iPhone 5 I use there is 9mm off the table, right? Now, I'm not taking focal length into account here. I'm not adding that into this here. But just to do some basic calculation. So that would be 9mm is 0.3543 inches, right? The table is about 2.5 foot, could be a bit more, but we'll just go with 2.5 foot, which is 30 inches, right? So 0.3543 inches divided into 30 inches is 84.66 times. So if I say my observer height is 6 feet above the water, right, and I multiply my observer height by 84.66, let's take it away from, let's say, make this 9mm my 6 foot observer height, right? Standing with my observer height 6 feet above the water, and I multiply it by 84.66, I'll get 507.9 feet, or 0.096 of a mile. So let's call it 508 feet, 0.99. Let's call it 508 feet. So a 25-foot object at 508 feet distance will have, why I'm saying a 25-foot object is because I'm saying that the phone charger, let's say the phone charger that I just showed you there. Let's say that's, I'll just go back. Let's say this is my eye height and it's 6 foot, and the phone charger is 25 foot. Now, it could be more than that, but let's just say 25 foot. It's probably a bit more than that. But let's just say 25 foot, right? Right, so a 25-foot object at 508 feet distance has an orthographic angular size of 2.81 degrees, right? So would it be that this, when it's back here, that, right, back here, when it's, that it would have, for me, an angular size of 2.81 degrees, right? Would a 25-foot object, if that was, let's say, 25 foot in relation to, I should have, you know what I mean? I don't know if it is 25 foot, but something like that. So if we move that back to, right, then the angular size of that is 2.81 degrees, right? If that was 25 foot, and this was 6 foot, right? So if that's 2.81 degrees, how do I expect it to stay the same height? Do you know what I mean? As it was, you know, in perspective view. How am I expecting myself to still have to look up to the top of it? Because if I was trying to look up to the top of this now, and this was my eye line, and I tried to look up to the top of it, right? Now, I actually should have probably given it more, probably 40 feet or something like that, probably be more like it. But if I was trying to look up to the top of that now, right, and then as it moved away, right, as you can see, the top of that is coming down. So my angle up to the top of it is less than what it was. That's all that's happening. It's purely perspective based, right? So instead of this, so if this is, let's say, 40 feet, and it moves away 507 feet from me, then I would say it probably have an angle of about 3 degrees, something like that. But the point is that my angle to the top of that has changed. My angle up to the top of that has changed dramatically. Why has it changed? Because it has appeared to come down. Its base has stayed the same. The earth hasn't come up. It's an apparent thing where things appear to come down, right? That's all that's happening. So if that was 25 feet, then it would have a 2.81 degrees size at 508 feet away from a 6 foot observer. Do you know what I mean? So, like, I'm looking at something that's 2.81 degrees. How do I expect my eye line to, how do I expect my eyes to have to look up at a 75-degree angle at that? It makes no sense. But I don't know, people just can't seem to get it. On our opposing side, this is something that completely, boggles their mind. You know what I mean? I don't know why this is such a problem for them, but they have major problems. 1 second, I'm just going to do something here. So, I say 508 distance, and let's say 40 feet. So, angle, degree, calculate 4.5 degrees, right? So, even a 40 foot, something that's 40 foot at that distance will have an angle of 4.5 degrees. That's not very much, is it? 4.5 degrees, that's probably what we were seeing here, right? Probably about 4.5 degrees, something like that maybe. Like, that's not much. How do we expect to keep on having to look up at it? It's naturally appearing to come down. It's not going over our curve. There's no our curve on the table. I've shown before in the past that this table I've shown it to be level, horizontal, and shown all this. This is all way past back in the old days. Shown all those things. The only reason that the top of that is coming up or going down is because of perspective. It's purely apparent. It's not our curve. No nonsense like that. It's purely apparent. I'll end the video here because I didn't realise it was going on so long. Thanks for watching it. I don't know if you'll all watch all of it, but there is no mystery here. It's just perspective. The person who made this understands that perspective exists, yet doesn't understand perspective and thinks it's our curve. That's all I could say. Thanks for watching. I know it's been long. Bye.